Hello, Eastview scholars, and our topic of discussion today is homeostasis. This is a key concept in anatomy and physiology, and as we have discussed, and as you can see by the definition, homeostasis is balance. You, like all living organisms, are a dynamic living thing. You are never static. You are never sitting in one place. There is constant metabolism, maintenance, replacement, rebuilding of cells, breaking down of foods. There are things that are going on constantly. And through all that, you need to maintain a stable environment. You need to maintain a stable temperature. You need to maintain stable levels of different chemicals like glucose and calcium and sodium and potassium in your body, amongst other things. And so a lot of the physiology we talk about and a lot of the systems that we look at, the homeostasis is key. Once it gets out of that homeostasis, then you have issues. You have illness, you have disorders, you have disease, you have what your book likes to call a homeostatic imbalance. And what we're going to look at here is what is that in terms of how is it regulated. Okay? First thing we have to look at is there is, and this terminology kind of can change slightly depending on the book you read, but a sensor, a receptor, a something that is monitoring or is sensitive to that change that is going to affect that system, or, and many times, multiple systems. There's a control center and integration center that processes that change and sends out commands of what to do. Oftentimes it's the brain, but it's not always the brain. Okay, and then there's an effector. Okay, that is the organ that responds and does what it does to this. Now here it says to oppose the stimulus, but that all depends on if it's a positive or feedback. But it does something to keep the homeostatic balance in line. This slide also says there's a set point. Really, that's your range. Where do you want to keep this thing? You know, temperature. Everybody believes their temperature is 98.6. Well, that's kind of the range. That's the average of human beings, but really some are lower, especially younger kids, or older folks are a little lower. Young kids and babies are higher based on metabolism rates and heat generated and growth and things along that line. You can think of that, one of the most common examples is thinking of that as your heating system in your house. You have a thermometer, a thermostat, or something that measures the temperature. Okay, you have a thermostat, a control center that says this is the temperature we want it to be, and you have an air conditioner that when it gets too high turns on and then will bring the temperature down. Of course, then it gets down below that temperature and the air conditioner will shut off and the room will keep going up. And that's what we mean by being dynamic, that will constantly flow up and down and stay in that relative range around the set point. Okay. Now, like I said, it's a range. It's not exact because it's constantly fixing things. It's constantly monitoring, and you might be in this narrow strip of a range. As you can see here, with the room temperature, average room temperature about 22 degrees Celsius. It's a little low. It's hitting a little low. Getting out of that, air conditioner turns on, air conditioner turns off around that set point. But it's just oscillating in between the temperatures that you want. Okay, and it does that by feedback. Now there's two feedback mechanisms in humans and in most living organisms. The vast majority is a negative feedback. So whatever you're measuring, okay, blood glucose, sugar in your blood, for example, as that glucose rises, then you'll have a triggering effect to bring it back down. And then as it gets down, you'll have a triggering effect that'll bring it back up. And you're constantly flowing in this range for your blood glucose, but you're never set. But negative means it opposes what's going on. So blood sugar was going up. We did a trigger that brought it back down. That's the negative feedback. Calcium levels in the blood, same way. As they get too high, that stimulus that says we're too high, the effector organ on orders from the control center make some sort of adjustment or trigger some cells and organs to bring it back down. Really all they do is kind of uptake the bones uptake calcium, muscles might uptake a little more calcium, and then the calcium levels in the blood go down, and then they dip down low, and a trigger is to bring them back up. Negative feedback. Okay. Here's an example talking about body temperature. Normal body temperature about 37 degrees. Relatively inactive. You can do some stuff, but that homeostasis is disturbed. If the body temperature goes above 37 degrees, okay, skin and other activities, you know, your skin, the vessels will dilate to release more heat, get it closer to the skin so more heat can be released. You can start sweating to have evaporative cooling, but that's the signal is the temperature is getting too high. It goes to the brain and it says to do these things. Smooth muscles, fine skin and sweat glands. Vasodilation occurs, and then it brings the temperature back down. Of course, then if the temperature gets a little too low, that's going to be different. You're going to have vasoconstriction. You're not going to be sweating. Vasoconstriction is going to pull the vessels away, the veins away from, make them deeper in the skin, and release less heat. So as one goes up, the other goes down. Your other option, which is a smaller number, only really a couple in humans, is positive feedback, where it enhances the response that's going on, exaggerates and enhances that change in the original conditions, and brings it to completion by pushing it. And the big one is clotting mechanism. The other one is breastfeeding and milk production in the mammary glands. But if you think of clotting, if you cut yourself, then what happens is blood rushes to the area, because the blood, being your transporter, your circulatory system, needs to bring the clotting factors and the immune system factors and the macrophages and everything that's going to keep you from getting an infection and help pack it up. So that's, you know, the sense is that the sensory portion is that you're losing blood volume, and it rushes more blood to the area. So it exaggerates it until it can fix it when all those platelets come and stop things. So here you see a little cut, a break in the blood vessel, damage to the cells, releases chemicals that begin the process. The chemicals start chain reactions in cells, cell fragments, and proteins and platelets start binding and clotting. And the platelets clotting creates more platelets to come and clot and accelerate, and pretty soon you have that blood clot, and you are not bleeding out. Anyhow, so that's a quick study of homeostasis.